No. Wow.
Okay, if you're not done, you should have it. You should be working on it. You should be thinking about it.
That's why you don't. Dude, you get graded out. What area? Do I have to write down that it's link? I was there to say it was. Yeah. My backdoor notes file. Oh, I thought we were talking about. You're using a logical fallacy of false dilemma. You either write it in the back or you don't. There's another option. You write it in
For those of you guys just joining us, either you're at the CSUN meeting today or Dean or Gavin, they've been pondering 48, 49, and 50. I have heard that 2 of them were on their homework last night, so they should have already put in enough time thinking through, and we'll see if they were right or not. And then the remaining one, we'll check it right now. So, here we go. For number 48, I can tell you the answer, but I'm more curious what you think it is. 48, what do you think it is? Oh, no. No one got it right? Hold on, raise a hand and give me what you think it is. Maybe I didn't hear the right answer. Raise your hand. Who has the answer? Miranda. Who else has the answer?
I have the answer.
Who else has the answer?
Mine's
Who
wrong.
else has the answer?
Say your answer. Say your answer, AJ.
Everyone's saying E? What do you think? C.
Well,
Anybody else have an answer?
E, because she's like,
I have
I could see. Oh, no. Kevin, you definitely thought it was the Italian game.
No, no.
149.
I'm not sure
Not
about
exist simultaneously.
I'm not sure about
So one of them
it.
has to be false. Why did I?
Wait, no, critical points could be
Struggle. Well, we need to talk about this one.
Oh, wait, I completely ignored
Okay,
A.
well.
Okay, pause. What do we know? Continuous. So no vertical asymptotes, no holes, no crazy breaks, right? Decreasing the whole time, the whole time. The whole time, the whole time. Question. Is this one example of continuous decreasing?
Yeah.
Where would this be? According to the problem?
Critical point.
At the critical point, which would be 4. And what would be the derivative at the critical point? So C can happen. True? Question. Is this continuous and decreasing? Sorry, pretend that was fun. I apologize. Is this continuous and decreasing?
Yeah.
Yes. Everywhere but an infinitesimal point in space. No, it's decreasing. It would say decreasing the entire time. There is no domain restriction, discontinuity to break up my interval. It is decreasing the entire time. Question. Do I have a critical point? What's my derivative? So D can be true. True. F of 4 is neither a relative max nor a min. Can be true. Neither a max nor a min. B. Letter E. F prime of 4 must be less than 0. Guys, both of these contradict each other. You can't have that one being must be false and this one able to be true, or this one must be false and this one able to be true. So those, you guys had a logical fallacy. You can't be saying that B can be true and this must be false.
Wait.
That's what I was thinking.
Wait, you can't say, oh, here you go. You can't say this one can be true. I apologize. You can't say this one can be true and yet this must be false.
Yeah, I'm not sure I'm understanding
Because f prime of 4 is a vertical tangent, right? F prime of 4, DNE, if f prime of 4 doesn't exist, it's a vertical tangent, true? What kind of infinity is it approaching because of the function decreasing? Negative infinity. So if you just straighten it out if you straighten it out just a little bit, it's going to negative infinity, which means there are infinitely many ways that slope can be negative. I see. It's my bad. E is the right answer.
Oh.
So make your defense. Make your defense. What's wrong with my straightening out?
Maybe this will earn me participation points.
Pause. Did you guys hear what Patricia said? Okay, well that was pointless.
I heard it.
Listen.
I heard it.
Patricia, what you say?
say?
Oh, now you're talking, you still can't hear. Stop. Patricia, go.
It wouldn't be a critical point anymore.
What do you mean it wouldn't be a critical point?
Because in order for it to be a critical point, it has to not exist or equal 0.
What was I thinking about? What was my fallacy? My logical fallacy? When I started to straighten that out, what point was I putting it for? Not a critical point. I was putting it. This would be an example where my function is continuous and strictly decreasing, and my slope at 4 is negative. It's not a critical point, but what was I putting there? Oh, nobody? I was putting a pip. Yeah. I was thinking that my clue was a pip, not a critical number. That was my bad. If it was a pip and not a critical number, if f double prime could have been DNE or 0, then mine would have been closer in the sense of eliminating E as an option. And Joe brought up my other logical fallacy. I was thinking must be true, not must be false. I was thinking must be false when I was eliminating everyone else, but then I was thinking must be true for another thing. Yeah, so yeah. Although I did get a few of you guys who think C or D. Okay, number 49. So yeah, it wouldn't have been a critical number if it had anything other than 0 or DNE. Let's go down to number 50 just because that one is more concept-y and number 49 is going to actually take math, right? At least to some extent. Number 50. What's going on if my function is even and there's a local max at x equals a? What's going on with that? Which one? Who else? One. What does even mean? So whatever is happening at A, however it is happening, isn't the exact same thing as be happening at negative A? Good. So whether we have a sharp point or whether we have a smooth turn, it doesn't matter. That sharp point or that smooth turn will be happening exactly in the same spot to the left of the y-axis at negative A. Good. Okay, so number 49. Exactly to local extrema on its domain. Exactly to local extrema. What's one way that you could have gone about mathematically thinking about this? Don't give me the answer, but what's one way you could have thought about it? Okay, so you could actually go looking for who is f prime. That's one way. What's the other way?
Think of the shape.
Think of the basic graphs. Good. Now, maybe you might want to think about both. For instance, x minus 2. Well, you can eliminate him. Why? He only has one extremity. True. He only has a relative and an absolute min. Don't forget him. That doesn't help. And double check f, and we're talking about f. F goes with f. Yeah. Okay. Yeah. But now we have cubics that, well, could or I guess they're both positive. So maybe none, maybe 2, maybe tangent. Does he have any relative extreme? Forget him. X plus ln, let's just assume that maybe you're like, I don't know what ln looks like, what the x plus does to it. Okay. So we thought about a couple basic graphs in order to eliminate f primes. Okay, let's go ahead and think about what we have. So we have this one, which is 3x squared minus 6. We have this one, which is 3x squared plus 6. We have this one, which is 1 plus 1 over x, which would be x plus 1 over x. Okay. Who can we eliminate next just from his derivative? Oh, I guess I was thinking C is the most obvious one to eliminate. But just because if I try to find zeros, aren't they imaginary? That'd be a square root of a negative number. We'll forget him. If I find zeros of him, he at least has zeros, right? At plus or minus root 2. He has 2 critical numbers. What about this guy? He technically has 2. Wait, why just 1? 0 is not in the domain, right? Ln of x has to be greater than 0. So technically the only one that even has the possibility of this being true is going to be. That would be a strategic way of saying, like, okay, I don't have time to go any further, but could you do a sign chart and check and make sure that it really is that? Well, guys, if it's a cubic, wait, this isn't a guess. It's definitive. If it's a cubic with 2 horizontal tangents, it has to have this behavior, doesn't it? The cubic either has 1 or it has 2. That's all I got. Right? So therefore, it has to have 2 local extrema on it. Okay. Ebb and flow. Okay, like my mental capacity. Anyway, so we have a homework due today, true? But where are we going next? Mean value theorem. Oh. No wonder the homework's due tomorrow on MVT. Let's go ahead and go grade. Yep. Let's go ahead and go grade. Section 5.2. Oh, 5.1. Sorry. Let's go ahead and go grade section 5.1. Oh, whew, I was going to say, if that doesn't show up, I'm in trouble. Alright, there we go. There's number 4, there's number 8, there's number 14, there's number 24. Ebb and flow, it's a part of a popular poem. What poem is it? Ebb and flow. Ebb and flow. Alright, you guys can see everything? Let me freeze the screen for a second for you guys to grab down. 4 and 8 and 14 and 24. Oh no, they're using words. So do the AP guys. Not saying you had to, but so do the AP guys. Does their math, I should say, does your math match their words? Wait, are words non-mathematical? Does their math match your math? Does their verbal description match your algebraic work? Hopefully, yes. Abby, did I pass over a question? Do you have a question? Bemoaning life's estate. Okay. Understandable. You guys are seeing things like why EDT failed on number 8. Seeing things like number 14, having to consider a function and not just the endpoints because there are no endpoints. So the function behavior and the critical points. You're seeing something new called stationary points. Stationary points. They just said k prime equals 0, and there are no critical points that are not stationary points. What are stationary points? Well, if you're stationary, what are you doing? Pretty envelopes, no? You're just still, right? So if you're still, doesn't that mean that your rate is 0? Oh, when the derivative is 0, those are called stationary points. Oh, cool. Okay. New vocab. For you guys, anyway. New vocab. Number 24 was kind of low on the page, and we forgot to get it kind of high. You have your different intervals split up by your critical numbers. There are no endpoints. So the extrema, the local extrema, must occur at all critical points depending on the behavior of the graph. I might not have any absolute extrema. If you guys noticed, they went looking for local extrema if there was no absolute. They were kind of doing that full analysis of the function. The local max value happens at the point 0, -1. The value is -1. You guys did great on that multiple choice at the end of class yesterday. Number 34, the min value is 4. Number 34, the min value is 4. Whoa, they used a graph? Little cheaters. You didn't need to, though, did you? Wasn't there a way to maybe take derivatives of absolute value functions? Huh. Piecewise, I'm a little worried with you guys in piecewise. We'll come back to 34 in just a second, but otherwise we have 36 and we have 50. We have 36 and we have 50. Now guys, remember, they do weird sign charts. They do weird sign charts. They have critical points, and then they're talking about whether there are HTLs or VTLs or sharp points. They look at the behavior, and they're able to say whether they are local or absolute, and what those values are. It's weird though, it's weird. I'm not a huge fan. Number 50 is B. Number 34, what if you didn't use your graphing calculator? What was that function, guys? You should have it written down, right? K of x is equal to
X plus 1.
x minus 3. There must be a lot of nasty, like absolute value of u, u prime over absolute value of u, or hold on, absolute value of u over u times u prime, or u over absolute value of u times u prime. There would have been a lot of nastiness. Is there a way that we could have written this as a piecewise function? How would you split it up though? Because you see there are two different separators, right? So how would we deal with, just because I've been trying to show you a lot this year how to think in piecewise functions if it's easy, we would have to use both negative 1 and 3, right? So we'd have x less than negative 1. What else would we have?
X would be negative 1
and 3. And then, okay, what would be going on with my pieces? Remember, every time we see absolute value, it's either same or opposite. It's either just remove the absolute values or put a negative around the whole thing. What would be true for anything less than negative 1 for my k of x? What happens to my first absolute value if x is less than negative 1? Negative 2, negative 3, negative 4. Wouldn't this flip the sign, guys? So that would be opposite, right? What would happen to that guy? Negative 1, negative 2, negative 3. Yeah, that would also be opposite. Okay. How about the next piece? Yeah, pick a test point, right? How about 0? 0 plus 1, doesn't that just stay the same? But how about 0 minus 3? What about the last one? 4. Same. And then, why does that make things easier? Or why could it make something? What are we supposed to be thinking of on number 34? Maybe I'm totally wrong. I thought you were doing extrema. Are you not?
Yeah.
Okay. So if we're trying to think of extrema, don't we want critical points? Where are my critical points? Well, couldn't I rewrite this and say, oh, sweet, this is a lot easier. That's just negative 2x plus 2. You can't take a derivative of that real easy, right? And then that one would be 0x plus 4. My slope is 0. And then wouldn't this last one be 2x minus 2? You don't necessarily have to go graphing the function. You don't need your calculator. You can totally do it by yourself, even without using u over absolute value of u times u prime or absolute value of u over u times u prime. Like, these are easy little polynomials I could put together if I could just get rid of the absolute values. So you can do that by piecewises. So what are we looking for? Well, slopes. Yeah, when the slope is 0. Slope is 0 at
1.
Oh, well, see, that's not in my interval. Slope is 0 at 1. Aw, that's not in my interval. So are there any natural critical numbers? No. There aren't any natural. Well, the slope is 0 for this whole time. Okay, that's great. But if I can't find critical numbers the old-fashioned way, setting equal to 0, then maybe I have to think about, DNEs. And when will they DNE? Sharp points. And what's happening if the slope is negative 2 coming into 4, or going, sorry. I need to write my 0. If my slope is negative 2 coming into 0, or positive 2 going out of 0, those are not agreeing as I come in towards negative 1, or as I come in towards 3. So if I was doing my derivative, I would technically have negative 2, but not at negative 1. I would have 0, but not at 1. And I would have 2, but not at 3. So therefore I have to check out what's going on at -1, what's going on at 3, and what's going on for that entire constant interval. Well, if you just do a quick test, or if you take each of your pieces and say, hey, it's a line and it's hot and it's a line, you will see your absolute minimum of 4. You would have to plug in, but of 4 at, well, any point within that interval, -1. Are there any absolute maxes? Heck no. Why? They're lines. They're going to go up forever. Anyway, they used a graphing calculator. You did not need to. Are there any further questions that you guys need to talk about on homework? Evens or odds? Did I lose all your trust with number 48? No? No evens, no odds? We're good? 51? 51. Being serious. 51 was an exploration. Ooh, that sounds fun. Looks kind of like an FRQ-ish, right? Not that it would be an FRQ, but it's trying to take like a somewhat concept-y problem, split it up into A's and B's and C's. Okay. What did you guys get for letter A in 51?
No.
Why?
Because when you derive it and you plug in 2, it's number over 0.
Yeah, when you derive it, you get a -1/3 power. You have a denominator number over 0. So therefore, does f prime of 2 exist? No, but how does it exist or not exist? There's a vertical tangent line there because f prime of 2. I can't say equals because it doesn't choose. No, I can because equals, it doesn't exist. That's okay. I would end up with 1 over technically 0, right? Which is my plus or minus infinity, check the sign, if I was doing limits, but the point is that's a plus or minus infinity, aka that's a vertical asymptote. So, my derivative has a vertical asymptote, which means my original has a vertical tangent line. Okay, letter B says, show that the only local extreme value occurs at 2. Oh, well, 2 is my only critical number, right, guys? Because if you hopefully found the derivative in letter A, you got your little 2 over 3 cubed root of x minus 2. The only crit is at x equals 2. Now, that's not enough to say it's an extrema, but my only crit is at the DNE, right? So how could I show? How do you guys show? Did you go to the second derivative, or did you go to the first derivative sign chart? Sign chart? Okay, so then with the sign chart, we have everything but our 2, which existed at the beginning, right? The beginning, the domain. X is okay at 2 before the derivative. So the derivative popped it down into the denominator, the x minus 2 factor. So he's okay. He exists from the beginning. But if I go plug in and chug in, if I go before, wait a minute, that's awkward. Well, I'm not plugging into my original, right? I'm plugging into my derivative. So if I plug in 0, a negative number cube rooted is a negative, and if I plug in 3, positive number cube rooted is a positive. If they asked you to explain, you would have to actually write that in words, that my function changes from increasing to decreasing at 2, or my derivative changes. Oh, I did that totally backwards. You guys tell my brain fried wasn't bad, we just did factoring huge polynomials and they get distracted very easily. Remember that we use increasing, decreasing with original quantities, and we use signs. Why are they having us do this? What are they trying to really trip us up at? Contradict a theorem that we've been told to memorize and say is true? Okay, hold on. Whoa. There's a relative min at 2, and the derivative does not exist because the derivative is not continuous at 2. But why does that not contradict the EBT? The derivative might not be continuous at 2, but that's not the theorem. The theorem just says who needs to be continuous at 2. And F was totally fine, as I kind of alluded to just a second. At 2, he's fine. So no, it doesn't, because I have F being continuous. Uh-oh. Hold on, struggle. What else is supposed to be true for EBT? On a closed interval? What kind of closed interval? It's a little bit awkward. I think they're technically probably talking about a corollary to EBT, so you just do continuous on closed interval. I think the main point that they were trying to say is that they were trying to confuse you and say, there's a discontinuity and there's a min? That doesn't make sense. Well, the main idea is no, f is continuous even though the derivative is not. And we look at those discontinuities because they can actually find first level extreme. And then letter D says, repeat for x minus a, replacing 2 by a, and then see what happens. For kiddos, all they're saying basically is that for any x minus a, aren't you going to have a local min at that a by the exact same logic? Does that make sense? So whatever that a is, x minus 2, x minus 3, x minus 4. Okay. It's a little weird. It's a little bit out there, but not impossible. Anything else from homework? Going once. Going twice. Sold on MVP. Go team. From all of your math knowledge. It's good reminders. It's green. I don't want you to rattle off the mean value theorem. That's no fun, because some of you frankly can't, and maybe you never could. And some of you can, and quite frankly, it's easy for you. It doesn't mean that you're going to be able to use it well, so help me out with the idea. Don't rattle it off for me. Help me out with the idea. Intermediate value theorem. Intermediate, in between, value, function value, y value, height value. You have a continuous function. Well, if it goes from one height to another, it has to pass through all the in-between heights somewhere. No guarantees how many times, but somewhere. Mean value theorem. Okay, fine. Math, mean. What do we think?
Average.
What do we know about average? Average rate, yeah, the slope between 2 points, right? F of b minus f of a all over b minus a. Average rate of, filled in, of f. To find the average rate of f, we use f values, not derivative values. Okay, average rate, sure, why not? Maybe that's a thing. Value. Well, hold on, we talked about this with local extrema, right? Value of, what are you thinking of? The y value, right? Like a function value, but what's weird in this one? Wait, right? We have seen a sec. Hold on, I'm putting it right here. I'm not putting it in. I'll put it down and forget it. Function value. Well, not this time. It's going to be a derivative function value. Mean value theorem. Yes, it's going to be a function value, but a derivative function value. It's a little bit different than the max of, min of in section 5.1. But still the right idea. Value is going to be a y value of the derivative. Mean is going to be average. And that leads us up to, well, the dude that we should already know, right? The dude that we should already know. So maybe you have him totally memorized. Maybe you remember he's in existence here. Maybe you remember in word problems, whenever you see something like must there exist, existence theorem. This guarantees existence depending on the conditions, right? Actually, you're going to be going to Mr. Rice's office, so please take up to Mr. Rice's. I think it's today, I'm assuming. Yeah, I should have put it on there. He's still on. Okay, mean value theorem. Mean, average, value, derivative value. Why does that help us with the formula, guys? Why does that help us with the formula? Well, don't I have average right here? My average rate is going to have to equal the value of for the instantaneous rate at some C within A to B. Oh, just kidding. Open interval. We had to see that a few different times last year because there would be ones at the endpoints and we had to exclude them. The whole differentiable thing, in case you've never really known why, you just kind of memorized it. Some of you, your brain's attached to a concept better if you can memorize why. If we have our A and if we have our B, this theorem will still work even if a function is not differentiable at the endpoints. I don't need it to be differentiable at the endpoints. I just need smooth turns inside. Now I need it to be continuous, because if it's not continuous, I might have a vertical asymptote, I might have a jump, I might have all sorts of stuff that messes me up. I have to be continuous at the endpoints if it helps. You can change the open and close to at the endpoints or not at the endpoints. So quick differentiable on the open interval is just because I don't care if there are sharp points at the endpoints, I just care about the smooth turns within in a very basic elementary type understanding of what's going on. But I can have sharp points at the A and B. I just can't have sharp points within. I can technically even have vertical tangent lines at the endpoints, I suppose, just not within. So then, you guys know why I had this homework tomorrow. MBT, we've seen MBT a lot. I mean, I can even throw up a picture that you might or might not even want to write down, but the idea of MBT is if I have endpoints, and I have endpoints where the function is continuous from endpoint to endpoint, differentiable everywhere in between, there must be some place where the slope will mimic the instantaneous slope, the tangent slope will mimic the secant slope, where the instantaneous will be the average. Where the instantaneous will be the average. And this makes total sense if we just think about it with our pumpkin farmer. Wasn't our pumpkin farmer last year, the former pumpkin farmer? If he was going 40 miles per hour, and then just a couple seconds later, he covered all this distance. He was going like 52 miles an hour. He was like, and then he passed the two different cops. How could they have nailed him mathematically? He covered way too much space in way too little time. His average rate was way above the speed limit, which means he had to go from his slower speed to his, well, even beyond that faster speed. But he had to go at least that average, if not. And on this example, we have a slope that's stinking high and a slope that's stinking low. He's going to have to hit all the slopes in between, but specifically, that secant slope is guaranteed at some point. But guys, remember, to have a guaranteed derivative, yes, we could use MBT, but more and more that AP is not just using MBT for a guaranteed slope. Remember, must there exist, what we're looking for MBT, must there exist a rate or derivative value, right? Intermediate value theorem is an original quantity value, an f of x value. MBT or Rolls is a derivative value. However, he's not the only way. Yes, MBT is one way. But remember, we can also use an alternate way of proving. Can also be using IBT with other derivative values. Do you guys just hear me or watch me use IBT? The average must be mimicked, yes. And if we have, like, for instance, a flat, if this were to come all the way down, that 0 would have to be mimicked, yes. We can also say, what is your derivative value? What is your derivative value? Prove the differentiability, aka all the derivatives exist. Sweet, IBT says a continuous derivative is going to have to pass through all the in-between derivative values somewhere. IBT can prove it too. IBT or MBT. Just a heads up. Because they might force your hand to use IBT. With that, oh, antiderivatives? Oh, that's fun. But first, why is that in the NBT section? That's weird. Pause. Ready, set. Why does MVT fail? What? I thought we were trying to use MVT. Well, part of using MVT is knowing when it doesn't work. Ready, set, go. Why does MVT fail? You can collaborate in your groups, I don't mind. Check out the function, the square root of x squared. Well, that's awkward. Plus 1? Yeah. Yeah, end the square root over the x squared. I know it's awkward, but end it. It does not go over the plus 1.
Is x to so that just ends up being x plus 1 derivative, which is 1, so you can plug it in. Wait, no. Yeah, that's x to the 2 is just x to the 1, and it's just x. Because 2 over 2 is 1. So it's x to the 1. Oh, it's not going to it's just x.
So you said that equals 0.
Over 2 minus 1. What are you
Okay, right. Okay, you have to.
Why is the x cubed?
No. Plus 1 is 2.
This.
And then negative 3x squared. 3 minus 1.
Absolutely right, sir.
Okay.
No. X or 2 over 2 is 1. Just so get rid of the 2 over 2 completely. It's just 1. It's not x to the 2 over 2. It's x to the 1, which is just x. So what's the derivative of x? 1. So stop doing this feng shui 2 over 2 chain rule. What's it called? Product rule. But technology is dealing with this problem. What? It's that the what's it called? I forget you might. It ends up being so that you can't plug into. So then it would be wait, no. Are you? Maybe I've been deriving this wrong. Alright, I'm thinking simplify it and then derive it. Because it's just x to the 2 over 2. That's 1. But what if you do 1 over 2 times x to the negative 1 over 2 times 2 over
only two things need to be true, right? Continuous and differentiable. His domain's all real numbers, so he's continuous, that's fine. Something must have gone wrong with his derivative. And when you guys took his derivative, did you get 2x all over 2 times the square root of x squared? What's wrong with that? Yeah, x equals 0, right? We're going to have a DNE of the derivative, aka not differentiable. And shouldn't you also have thought about how the square root of x squared is really an absolute value, and absolute values have sharp points? Anyway, coming back. For letter B, is this one continuous? How do you check continuity of a piecewise?
Plug in at 1.
Yeah, plug in from below and plug in from above, right? Coming in from below, that's 4. Coming in from above, that's 3. Well, forget that. That's a no, because I have a discontinuity where? x equals 1. Now, some of you might have thought it was continuous, and you started looking at its differentiable, right? Started looking at its derivative. I wonder if that's interesting at all. F prime of x. If they had made it really mean, the derivative would have matched up, and you would have been like, yay, it's good. But they weren't really mean, because check it. The derivative wouldn't have agreed either, would it, guys? And I'm not putting it or equal to, because if the derivative doesn't agree, remember, a derivative is a limit. So if it doesn't agree from both sides, like at 1, the derivative doesn't exist. So technically that also fails. But sometimes this can look like it works, but because of a discontinuity, it actually fails. So be careful. Always check continuous first.
Doesn't it?
But either way. Huh.
Doesn't it not matter? Like I'm.
This whole thing didn't matter. But I was saying some of you might have not realized that it was discontinuous and kept going, and so I just would have said, warning, there are times they could have done something, I don't even know how they would have done it, but they could have had like a 2 there and a 3 there, to where it actually would have matched up, and you might have accidentally said yes. But no, you're right, Joe, it doesn't technically matter, because failing continuity is enough to say nope. Now the weird thing is, our section ends on an antiderivative. What? Okay, I can actually, before we go talking about an antiderivative, which is the beginning of integration, which is weird since we're in an application of derivatives chapter, and we're in the NBT section. Long story short, NBT actually proves why that you need a plus C. Proves it. I don't mean like illustrates it. I illustrate with vertical translations and like taking lots of derivatives saying, of course there has to be a plus C. But what's really going on is, well, there's all these corollaries to MVT. There's a corollary 1, there's a corollary 2, and our book, this book, the thin book, decides in the MVT section to cover everything to do with increasing, decreasing. Yeah, they didn't cover that in section 1. Go figure, having to do local extrema without knowing increasing, decreasing. That's awkward. But corollary 1 from MVT is actually increasing, decreasing. Corollary 2 from MVT is actually over here underneath the other consequences section. Corollary 2 has to do with if the derivative is 0, then there has to be a constant the function equals. And then from that corollary, actually they build into, or they go into, talking about derivative values using that MVT. So long story short, there is an application of corollary 2 leading into corollary 3, talking about if 2 derivatives are equal, then there is some constant such that f will equal g, but possibly off by a constant. Anyway, long story short, MVT proves plus C. It's kind of awkward. It's kind of weird. But you guys get to enjoy homework a little bit because you're going to be playing around with some antiderivatives. And it's as easy as, well, guys, they're teaching it for the first time, but for us, it's just review. So the nice thing is antidifferentiation, finding the antiderivative, going backwards. What's the antiderivative of 2x? X squared plus b, right? Nice. Any function that has a derivative of 2x, they all had to come from x squared. The x squared that might have been off by a constant. NBT proves it. You can read the book to see why. It's not my purpose. It's not my objective for you guys to know how to use NBT to prove why this is true. It's cool. We can use it and we'll play with antiderivatives as a result in our homework. So what's the antiderivative of, do you remember how to do antiderivatives? 5x to the 3 halves? 2x to the 5 halves plus c. Another way of thinking about it is the 5 times 2/5, right? X to the 5 halves. And as Lainey said, yes, the 5s would reduce, and yes, you would be left with 2. And hey, remember the x to the n plus 1 all over n plus 1. So, it's a little weird. And they don't cover all the anti-differentiation rules. Oh, P.S., by the way, in this section in our very short, small, condensed book, they also decide to go through motion and do velocity and position because of MVT. It's weird. So who knows what you're going to see in homework, but for us right now, I think that's enough. Sound good? Google Classroom, if you want to write down the assignment, let me get it for you. Google Classroom. Unless my computer freezes. Wow.
You actually did this as a hierarchy move to make sure you won the video.
Yeah.
Maybe I just minimize things. Oh, here we go.
Me, myself, and I. Actually, going to the homecoming board meeting during debate club.
Oh wait, we already have this one. Where's number 15?
Oh, right.
Here, I'll stop it.
You'll go for me?
No, it's cheating.
Can I let you take my place on the homecoming board?
Oh.
I'm sure everyone would love to see Joseph.
More people was Ryan voting. Therefore, Ryan, people would rather see Ryan. People want Ryan.
All right, here you go, guys. As we debate the homecoming court. There you go. If you guys want to write it down in your homework spirals or take a picture.
As long as the football game isn't during the scorching heat during the day.
No, you have to wear a suit in the scorching heat.
Yay! Suits in scorching heat. Bye, guys. Anybody else writing it down? No. Yeah.
See, I have a meeting today. I'm coming home.
President.
No.
Just lost your pen.
Sad.
I just lost my
You just accidentally left